Hello and welcome to Wednesday's lecture for week 15. This is the last lecture of the semester. We're talking about recursion, which is section 5.6 of your text. And section 5.6 is long. It talks about a lot of things having to do with recursion. It goes into Fibonacci sequences and compound interest and so on. It's a good read. But these are the 5 things that you absolutely need to know, especially in order to finish the homework and to do well on the final. So the 5 things, starting from finding the terms of a recursive sequence up to finding the limits of a recursive function. So to find the terms of a recursive sequence, we first have to be given the first term. It's just like the proof by induction. You can't do anything unless you prove that it's true for the first term. We have to be given the first term. In this case, we're given that the first term of the sequence is 1, and then to find the next term of the sequence, you just, for example, if you want to find B2, in place of your dummy variable k, this could be anything, k, j, n, you plug in the number 2. So b sub 2 equals b sub 2 minus 1, which is just b sub 1, which is your previous term, plus 5 times 2. So that gives you 11. And then to find the next term, b3, you take the previous term, which is 11, and then you add 5 times 3. So 15 plus 11 is 26. So I think you'll find finding the terms of a recursively defined sequence to be easy, provided you're given the first term. Showing that a sequence satisfies a recursion relation, this is also relatively straightforward. If you are given the sequence and you have you have to prove that it obeys this recursion relation, then we start with the right-hand side of the equation here. We compute this b to the k minus 1 term by just using our definition of the sequence. So here's our dummy variable again, right? Instead of k minus 1, we're going to make it n minus 1. Or, sorry, the other way around. If I want to find the k minus 1 term, then I substitute k minus 1 for n. So here, instead of 4 to the n, it'd be 4 to the k minus 1. So my b sub k minus 1 term is 4 to the k minus 1. And now I can just substitute this k minus 1 term into this equation. 4 times this thing that I just got for the k minus 1 term using this sequence definition gives me, when I do a little bit of algebra, 4 to the k. So this is the same thing as b to the n. b to the n equals 4 to the n. So I've shown what was to be demonstrated. Finding recursion relation, recurrence relation. I think this is I should have said recursion relation. This is probably the most difficult part. It requires you to really kind of engage your cleverness. And I wanted to show you one way to do the problem that deals with the realistic Fibonacci sequence. So in this new Fibonacci sequence, we're saying that one pair of bunnies actually makes 4 pair of bunnies after the first month, because they don't reproduce their first month. So after the first month, you still have 1 pair of bunnies because they didn't reproduce. After the second month, then we look at how many bunnies there were 2 months ago. Well, there was only 1 pair of bunnies, and each pair of bunnies makes 4 new bunnies. So that means we have 5 pairs of bunnies. 1 plus 4 is 5. So then on the next month, we have 5 is how many we started with, plus 4 times the number of bunnies we had 2 months ago, because remember, they don't reproduce their first month of life. So this is 5 plus 4, 9. Then my next term, it would be 9 plus 4 times however many bunnies there were 2 months ago, so that's 5, 4 times 5. Okay, so you're starting to see that recursively it has to be defined like this. It has to be the previous term plus 4 times however many pairs of bunnies there were 2 months ago. Alright, and using induction to prove a recursion relation. There was actually a lot of new stuff built into this example, and so I wanted to go over those new things and also to review the old thing. And the old thing was, how do you do proof by induction? Well, remember, I think that was just last section, right? First, you show that if it's true for one term, it's true for the next. And if it's true for the first, then it's got to be true for all. And you just say, therefore it's true for all by induction. And hopefully this makes sense to you now. If it doesn't, please go back and look at the previous lecture on proof by induction. Actually, it was 2 lectures ago. So this is our task, is to show that if it's true for one term, it's true for the next. In order to do it for the problem in the text, we have to know a little bit about the greatest common divisor, or the greatest common factor. In other words, how to find it. So when you see this GCD term, it's exactly equivalent to the greatest common factor, because a factor and a divisor are kind of the same thing. So the abbreviation for greatest common divisor is GCD, and the lemma that's given to you in the book is that the greatest common divisor of two numbers a and b is equal to the greatest common divisor of two numbers b and r if a is equal to b times the quotient plus a remainder. So if you just turn a, turn a into find the quotient and the remainder of a after you divide by b, in other words, then you get the GCD of b and r. So let's this is actually called the Euclidean algorithm, if you want to look that up on YouTube. There's a few examples showing you how to use the Euclidean algorithm to find the greatest common divisor. So let me just do it for a simple one, like 16 and 12. So here I'm saying that a is equal to 16 and b is equal to 12. So I want to be able to write it like this. Right? I'm going to divide 16 by 12, and I'm going to get a remainder of 4. 16 divided by 12 is 1 with a remainder of 4. So you see how I've just written this 16 in this form, in quotient and remainder form. Okay, well, using this lemma, I know that the greatest common divisor of 16 and 12 then has to be equal to the greatest common divisor of this b term, which is the smaller of the two numbers, and the remainder. So in this case, the b term is 12 and the remainder is 4, so it's equal to the greatest common divisor of 12 and 4. Right? So the greatest common divisor of 16 and 12 is equal to the greatest common divisor of 12 and 4. And probably you can just look at this and it leaps out to you that the greatest common divisor of 12 and 4 is 4. Because if you look at the divisors, or the factors of 12, you have 1, 2, 3, 4, 12. And the factors of 4 are 1, 2, and 4. Well, the ones that they have in common are 1, 2, and 4, but the greatest one that they have in common is 4. So I think that it's kind of obvious from this step, but if not, and quite often it's not from the first step, you just have to kind of do it recursively. Do this again. Now let's find the greatest common divisor of 12 and 4. So I take 12 divided by 4, I get 3, quotient of 3 with a remainder of 0. That means that the greatest common divisor of 12 and 4 is equal to the greatest common divisor of 4 and 0. And now it's obvious that hopefully I should never say that, but now it's clear if you know this thing, that 0 has an infinite number of factors, right? 0 and anything gives you 0. So the greatest common divisor of any number and 0 is that number. So the GCD of 4, 0 is just 4. Well, that's equal to the GCD of 12, 4, which is equal to the GCD of 16 and 12. So we've found the greatest common divisor of 16 and 12 by doing this little recursive step until we have 0 in the R term, right? Because then that tells us that the greatest common factor is the other number. Okay, so let's do that to prove that the consecutive terms of a Fibonacci sequence have no common factors other than 1. And a way to write that, I kind of tilted here. The way to express that mathematically is that the greatest common factor, or the greatest common divisor between the next term of Fibonacci sequence and the previous term is 1. They have no common factors other than 1. So our first term, our first task when we're trying to prove things by induction is to show that if it's true for this, it's got to be true for the next term. So what is the next term? Instead of n plus 1, it'd be n plus 1 plus 1, which is just n plus 2. And instead of f sub n here, it'd be f to the n plus 1. So my task is to show that the greatest common divisor of f to the n plus 2 and f to the n plus 1 is equal to 1. So here I can just use the definition of the Fibonacci sequence, which is that one term of the Fibonacci sequence is just equal to the sum of the previous two terms, to rewrite this first term as f to the n plus 1 plus f to the n. Well, this now becomes the a of my GCD AB lemma. Right? This is a, f to the n plus 1 plus f to the n, and this is b. Well, notice if I write it like this, that my b term is right here. So it's really easy to divide these two because you know that it's my a can be expressed like this, which is just my quotient is this 1. So my a can be expressed like this, which shows that the remainder is f to the n. And then I can, therefore, using this lemma, I can just write, since this is the b term, f to the n plus 1, and this is the r term, this gives it, this is br, right? This is ab, and this is br. So I've shown that the greatest common divisor of the next term, the f to the n plus 2 and f to the n plus 1 term, is the same as the greatest common divisor of the n plus 1 and f sub n term, which is what we were trying to prove. And remember, the first step, or the last step if you do it my way, of proving something by induction is showing that it's true for the first term. And for any recursively defined function, you have to be given the first two functions, and Fibonacci sequences can be defined from any two starting numbers, but using the traditionally defined way to define the traditional starting terms for the Fibonacci sequence are 0 and 1, or 1, 1 if you prefer. And that gives you the greatest common divisor between 0 and 1, or 1 and 1 is 1. So it's true for the first term, and if it's true for the one term, it's true for the next, therefore it's true for all by induction. And the last thing I'd like to go over is how to find the limits of a recursively defined function. And I'd like to just do 3 examples to show you this. And what all of these limit problems come down to is recognizing, well, I guess 2 facts. The first fact is that if you are taking the limit of this function a sub n, it's the same as the limit of a to the n minus 1, because these are defined in the same way, right? To find a to the n minus 1, you would go a to the n minus 2 plus 10 over 2, right? So that's one of the keys, is recognizing that both of these, a to the n's and a to the n minus 1, have the same limit. In the limit when n approaches infinity of a to the n is the same as the limit when n approaches infinity of a to the n minus 1. Because if n is infinitely large, then a to the infinity minus 1 is a to the infinity, right? So these are the same number, L. And that's our task, is finding this limit where n goes to infinity of a sub n. So if I take the limit of both sides of this, I have the limit as n approaches infinity of a sub n on the left, and on the right hand side I have the limit of all of this. And if you want to find the limit of all of this, really the only thing that changes is this term. That means I can kind of distribute the limit, if you will, right? The limit of all of these terms, these constant terms, stays the way they are, but the limit of a to the n minus 1 becomes this, which, hopefully you'll agree, is L, right? It's the same limit. So we have L equals L plus 10 over 2, which is just an algebra problem. You can solve that for L, and you get that the limit is equal to 10. I think that's pretty cool, right? It's not obvious from the nth term equation that this limit is 10. Okay, let's do 2 more examples. One where I have to solve a slightly more complicated algebra problem. So here's my recursively defined sequence, and I'm given a first term. I have to be given a first term, as it turns out, to tell which of these 2 limits is going to be correct. So first term in the sequence is minus 1. Now I do the same thing. I recognize that the limit of this is the same as the limit of this. So my equation becomes L equals 12 over 4 plus L. Now I have to solve this. And if I multiply both sides of the equation by 4 plus L, I get this quadratic, and I can factor that out. And so those are my 2 roots. The limit can either be 2 or minus 6. So which one is it? Is it 2 or is it minus 6? Well, in order to tell, I'm going to take my first term, a equals minus 1, plug it into my recursive function, and I notice that 12 over 4 plus minus 1 is 12 over 3, which is 4, so a positive number. And now let's look at the next term. I have a positive number in the denominator, so I'm going to get a positive number for this quotient. and I'm going to get a positive number for every term after that. Therefore, my limit can't be minus 6, so it has to be 2. And finally, this one's very similar to the homework, is let's find the limit of a to the n as n approaches infinity, where my recursively defined function is this, the square root of 6 plus the previous term. Well, remembering that this limit is the same as this limit, this is my algebraic equation. I can square both sides now. I get L squared on the left-hand side and 6 plus L on the right. And I factor this and I get 3 and minus 2. And now I know it can't be minus 2 because when you take the square root of a number, you can't get a negative number. So, actually, that's a little bit of a lie. It's the principal square root. Yeah, the principal square root has to be positive. So L is equal to 3. Okay, well, I hope that helps with the homework. It's been a real pleasure teaching this class with you guys, and I hope to see you. Well, I guess we'll talk more before the final, but I hope to see you next semester.